So like absolute max or absolute min is smallest value, largest value. There's nothing like too exciting about that. There another way they call it is extreme values. So it'd be nice if they just stuck to one vocabulary word, but they don't. So just kind of know that's interchangeable. So like an absolute is this is the absolute max because it's the biggest value on the curve. The absolute minimum is here because that's the lowest value on the curve. That's it. Okay. The locals are like the humps, on the curve in a way. So like local or relative maximum technically is the largest value on an interval. So basically like a local max would be here because it goes from positive, negative, max here, positive to negative, local minimum here. So it's never an endpoint. Okay. For Mott's theorem, they never have you prove that. So it's basically if you have a local max or minimum and the derivative exists, then the derivative equals zero. They'll probably throw that on a multiple choice, but they're just saying like we know for sure it's a max and a derivative exists. So if it's a local max and the derivative exists, the fact that they say that the derivative exists means that it eliminates the corner. Okay. So like if you know it's a maximum and it's the derivative, then you can assume that there's a horizontal tangent. Okay. Critical number, what people mess up on this, everyone remembers that one. The derivative equals zero, but everyone forgets the does not exist thing. Okay. So like this is a local minimum. This is a local maximum. This one, the derivative equals zero. This one, the derivative doesn't exist. So just be careful with that. So critical numbers, local max and min, that's like the same thing in a way. So why do they have all these extra names? Do you know what I mean? Anyone else? Okay. Extreme value theorem. Make sure you know this one pretty well. This is just saying if you have a continuous closed interval, there exists an absolute largest and smallest value. Seems kind of common sense to me, but it just has to be continuous. So you have to make sure, usually they say it's differentiable. So you have to say if it's differentiable, therefore continuous. And you have to say closed interval. It has to be on a closed interval. Because the graph you have to look at a chunk of the graph. So if there's an absolute, I want to do green because when we justify it. So continuous closed interval, there's an absolute max, maximum, and then minimum would be like the lowest value. Okay. Mean value theorem. We're getting all the theorems. Okay, this is the one where I remember the car. So this one is saying like I drove to La Crosse. My average speed was 70 miles per hour. Let's just say. Okay, so I'm driving to La Crosse. Average speed 70 miles per hour. What the mean value theorem means is like my speedometer should read 70 at least once on my trip. Okay, so if my average rate of change is 70 miles per hour, my speedometer, aka my instantaneous speed, should hit 70 at least once. That speedometer is a little aggressive, but this is like this part of it is like the speedometer. I don't know if that helps, or like instantaneous rate of change. Like my speedometer is going to equal my average rate of change. Okay, so your average rate of change is the slope of the secant line. Nothing's changed there. What the average rate of change is, you're just finding the slope. And then graphically, it means your tangent line is going to be parallel to it. It equals the same slope. So sometime on my trip, my average rate of change is going to equal my instantaneous. If I'm driving to La Crosse, that's going like waving a lot. Especially if you're buying a semi, then you slow down and then you have to speed up to go around. You know what I mean? So, all right. Okay. I tried to find weird ones for you. to identify critical points, because piecewises are always kind of like, you know. Now, use your brain on what this stuff looks like, okay? Like, use kind of like your common sense. Like, okay, we got parabolas, right? Squared, x squared. But do you see how they're both negative? The negative x squared, so what does that mean? They're parabolas and you got a negative on the x squared. They're going to be opening down, right? So, like, if they're both opening down, kind of trying to picture like different ways that could look. Because that could look like the M. Do you know what I mean? Like both of them. Because it's getting screwed up at one, right? They're switching over. So like I'm trying to picture like how that would look if you're dealing with two parabolas opening down, right? So kind of have that like in the back of your brain on when you're doing these things. So it says identify critical points first. So I guess we got to do that. So critical points is when the derivative equals 0. So that's like easier. Actually, why am I calling it f? It's y. Okay, so the derivative equals 0 or the derivative doesn't exist, right? So what you should do first is it's a piecewise, right? So think about if it was the two parabolas facing down, right? We could have a corner going on. Do you get what I'm saying? Like we could have like this thing, you know what I mean? Like once they meet up at 1. So this could be a local minimum. Do you know what I'm saying? So what I want to do when I have a piecewise is check for a corner, aka make sure that this thing's continuous at 1. Because that's what's going to happen. It's either going to be a discontinuity at 1 or it's going to be like it'll be continuous, but it'll end up being a corner. So the first thing you have to do is just show that if you're going to take a limit, it's already not going to be nice to me today. Usually first hour, it's got the glitches figured out. But anyway, okay. So we're going to go at 1 from the left and the right to make sure it's continuous there. Okay, no, I don't want that. Okay, so if you plug in 1 in the top function and the bottom function, what do you get? 1 for this one, and this one is 1, right? Okay, yeah, not going crazy. Okay, so it's continuous. Okay, so we're good, but then what's happening is x equals 1 is probably where that corner is going to be. So we're going to check it when we're trying to figure out extreme values, okay? All right, so then I did the corner action, but then now I'm going to do the derivative equaling 0. So then what I'm going to do is I'm going to take the derivative of the piecewise. So that's how you would write it. You would just do derivative, and you just take the derivative of both of them. So you do negative 2x minus 2, negative 2x plus 6, and then that's when x is less than 1, x is greater than 1. So you just take the derivative of each, and then now what you're going to do is figure out when those derivatives equal 0. So we did the does not exist, so this is the does not exist section, okay? Okay, so we're thinking that's a corner, and sure enough it is, because look at this, the two lines. They don't match up right away. So then what we're going to do is we're going to set this top one equal to 0. So what is that? Negative 1. And then the bottom one equal to 0. So that's 3, right? Okay, and then now that I've got like all my critical x's, what I'm going to do is figure out my local extremes. So for local extreme values, this means I'm going to find like a y value. Okay, so we're not dealing on a closed interval. That's why they're asking for the locals. So they're trying, I'm guessing these two like hump things in the corner, they want to figure out what those y values are. And again, we're dealing with local because we don't have an interval. So this one I just made a chart. And I'm going to check -1, 1, and 3. And basically you're just going to throw them in the right equation. So you're going to plug -1 into this top one. +1 we kind of already did. We're over there. Actually, I'm going to just put that in right away. And then 3, I would have to plug in the bottom one. So if you plug -1 into the top one, what is that, 5? And then if you plug 3 in, you get 5 as well. So then your minimum, your local minimum would be here. And then these are the same. So there's 2 local maximums. So does that make, is everyone okay with it? Does that make sense with it? Okay. All right, so piecewise can be weird. Again, think of using common sense of what these look like. Not common sense, but your math knowledge to figure out what they look like, to see what could happen when like 1 happens, you know? So you want to figure that out. See, make sure it's continuous, because then you can assume corner. Okay? Then the derivative's like normal. It's just now you're doing it double time, essentially, to figure it out. Number 2 is just weird, because it's like, you're like, I don't even know what the heck that looks like, right? You know, but really what you would think to do is the answer. So like this one, like, okay, extreme values on an interval. So what that means is I got to check endpoints, which that'll be easy. I'll just plug in -5 and 5. But then the derivative is kind of like, you know, like if you did f prime, you're kind of like, what do you do? You know what I mean? Because you're like, how do I take a derivative with bars? Right? So the way you approach this with like kind of goofball functions is you want to figure out when the derivative doesn't exist. That's the key. And again, knowing things about like math, okay? You know how absolute value graph has, it's like the V thing, right? So if there's a V, okay, that means we've got corners going on, and the corners are exactly where you would think. So like, even though it's like an addition situation right there, what you're going to do is, your corners are exactly where you think. 2 and, why did it disappear? -3. Is it going to appear? There we go. Okay. So this is where your corners are. So for extreme values on absolute value, you need to be looking for that, or think about that. Okay, so the first thing is you figure out if your derivative equals 0, then denied, and then derivative doesn't exist. Okay, then your second step is you're going to make your chart. So you're going to plug in your x values and then f of x. And then you have to make sure that you're checking your endpoints, because remember Robbie's lowest point was an endpoint. So you want to check -5 and 5. But then you also need to check like your fancy points. So the corners could be the lower part. We don't know for that one. So that's where you're just like straight up plugging in. Like you're plugging it into regular f of x. So you're plugging -5 in, and then you're plugging -3, and yada yada. Yeah.
Isn't there like a point though, like when there's a corner like in between them, you know what I'm saying?
Oh, no, I mean, if we graph it, you'll see what I mean. But like, no, there shouldn't be. Because we should, I'll show you in a sec. Because of the interval, it works out too. So with this, if you plug them in, it would be, what did you get? 9, 5, 5, 11. Is that what you guys got? So then you would say for step 3, you would say, so on the, if you were to explain it, okay, usually they don't expect an explanation, but you would say, since f of x is continuous, on the closed interval, negative 5x 5. Or you could put that in interval notation. It's absolute max. It's absolute maximum is just the biggest number. So what is that? 5 comma 11. And, or actually they usually write it like this. F of 5 equals 11. And absolute minimum is at, and then it's the same number, right? So you're kind of like, well, shoot, what am I supposed to do with that? So you're going to go F of negative 3 equals F of 2 equals 5. That's what I do. So I just keep doing the equal signs and then it works out. Okay. Oh, my calculator is messed up. I'll graph it once I can get my stuff situated, but I'll put that graph up in a second. All right, next one. Must there be a value C at which h of x attains an absolute maximum on the closed interval negative 3 to 4? Justify your answer. Okay, so must there be a value C? So that's clue that you're going to have to justify some stuff. Okay, absolute maximum on the closed interval. So what you need to check for is the first thing is you need to check continuous. Okay, we already have the intervals, so we should be good here. But what you need to do is check for continuity. So for continuity, just for practice here, so the first step is continuity. So you want to make sure h of 2 exists. You need to figure out the limit as x approaches 2 from the left of h, from the right of h, and then make sure that those two equal. So if I plug in 2, I get 2, I think. Yep. And then from the left, if I plug in 2, I think I get 2 for that one and 2 for that one. So therefore, the limit as x approaches 2 of h equals 2, and then my money step is this guy. Okay, so continuity, remember this is like within that, you have step 1 saying that your function exists, the limit exists, so you got to do the left and the right so it equals, and then step 3 is saying that your, not F, what am I doing? That your value at 2 equals your limit. So when you're going to say, you don't even need to like find it. It says, must there be a value C? So basically you would say, since h of x is continuous on, and then the interval is just from the problem. I usually just copy what it says up there. Then you say, by the extreme value theorem, then you say there must be a value C, which h of x attains an absolute max. I just recopy what's in the problem. So you're going to say h of x is continuous, and you'd have all this work here on the interval by the extreme value theorem. And then now I'm going to say so I'm just going to rewrite this. There must be a value C such that h of x attains an absolute maximum. With notation, it's possible they'll show you this. Another way you could write it. That's another way to say an absolute maximum. Whereas like if I plug in C, it's going to be greater than or equal to all the other values on X. They might throw that at multiple choice, but I don't know. We'll see what happens. Is there any questions with that? Because you'll probably have to do that again sometime, somewhere. Do you know what I'm saying? Okay. Happy Monday, hey? Okay. Now, this one, the function f is continuous on a closed. Why don't you think about this? How about that? You should think about that one. Oh, this is the one I was talking about. Okay, think about that. Does anyone feel confident? Yeah? 4. Any other ones? Yeah, 2. Yep, 2. So 2 and 4. Yeah, because the minimum value of f is -6. They didn't say local. Okay, so that's the part. Yeah, we're not done. I'm sorry. We still got like 2 more. We have mean value theorem stuff. Okay. This one is they'll throw you at multiple choice. Okay. Find all values C that satisfy the mean value theorem. So they'll give you a rando graph. So if you go to mean value theorem, here's that picture. Remember, this represents average rate of change. You just take the endpoints, draw a line, the slope of it. The instantaneous is parallel to it, but a tangent line. Okay, so if they give you a picture, what you do on your multiple choice is draw the line between the ends. Okay, and then try to figure out how many tangent lines would be parallel to it. So like here, looks like this guy would be tangent and this guy would be tangent. So what are the values C that satisfy? So C equaling about 1 and 3 would be those two values. It's when the tangent line is parallel to the average C, the rate of change on the average. Okay. Okay, and then we've got a justifying one. So table below gives you values. Is there a value C on the interval? Well, h prime of C equals 3. Be careful with this. Pay attention to the fact that you have h values and you're talking about h prime. So that's going to be mean value theorem. If you had h prime values and they were asking about h prime, that's going to be intermediate value theorem. Okay, so you have to make sure that whatever stuff you're given, you're doing the derivative of it for mean value theorem. Okay, so the way you do this is we've got, is there a value C on the interval? Well, we first have for mean value theorem, you would have to say since h of x is, so for mean value theorem, you need differentiable, and you've got it, is differentiable on the interval. So on the interval 0 or 3, 9. Okay. And now this is the part where I check that the average rate of change equals an instantaneous. So what I'm going to do is find the average rate of change and make sure it equals 3. So, oh no, 3 to 9. Oh, phew. I started doing 0 to 9 and I was like, wait a second, that's not going to equal 3. So, okay, between 3 to 9, hopefully that works. So I'm going to show the grader. I'm plugging in 9 and 3 and I'm doing slope formula. Okay. So then when I plug that in, I get 13 minus -5 over 9. Well, I guess I could just actually subtract that. We get, go away, 6. And then here we go, 18 over 6 equals 3. And then you have to say that that equals h prime of C, right? So this whole work is just enough. Just show your work underneath saying the differentiable on the interval. Do you know what I mean? Because then when you write this, you already got it covered, and say it doesn't equal, then you can just put a slash through it and be there by the intermediate value theorem. There is not a value C. Do you know what I'm saying? So like always start your stuff with like differentiable on an interval, then start showing the work, because then you can just put a slash without having to erase everything. And then you could say by mean value theorem, there does not exist a value. So you say by the mean value theorem, there exists a value C such that h prime of C equals 3. Is there any questions with that? Do you get what I'm saying? Where you could say no? Yeah.
Can you use like any combination of the numbers, right?
Yes. And that's when they can be really mean. Actually, that's your warm up for tomorrow. So like they sometimes just do the slope between 3 and 6 and you get 3, you know what I mean? Versus 3 and 9. So that's where it can get hard. Yeah. All right. So I don't know. I think. Do you want to do that one? Think about that. Which one does not satisfy the conditions? Might have to think pretty hard on that one. Oh, whoops. I did it opposite. What'd you guys get? Did you guys get C? Because if you plug in negative 1.5, you're still taking natural log of a positive. So it's still continuous. Because you're basically checking if it's continuous. Did you guys get it? It is differentiable. Yeah, you can take a derivative of that. Okay. Yeah. Ah! Okay, there you go. Hold on 2 seconds. Okay, so all of them you can take a derivative of, okay? But this one's discontinuous at 1. So there's an asymptote there. So that's why it doesn't satisfy the conditions. Okay, so because if it's not continuous, it's not differentiable. So that was like a sneaky way to ask continuity. So, all right, so there we go. That's it.